Okay, let me just move the, okay. Okay, well, thank you so much, Dale, for that nice introduction, and thanks everyone for being here today. I'm really excited to share some of my research. I'm gonna try to give a bit of an overview of the tools that I use in my research. And so the title that I have here is Ice Age Crustal Deformation and the Erosional History of the Channeled Scablands. It sounds like you all spend a lot more time in the Channeled Scablands than I do. So um, you'll, I think some of the pictures I show will look familiar. And so in this talk, I'm going to try to explain the research tools that I use in modeling Ice Age crustal deformation, and then
Dr. Pico, I think we maybe lost your audio.
oh no,
Now it's back.
oh, it said my internet connection was unstable.
Oh
So
dear.
it might have been the internet.
Okay, good.
Okay. Is, do I sound good right now?
Perfect.
Okay, sorry about that. And yeah, interrupt me if there's any glitches in the talk, and even if you just have clarifying questions, feel free to interrupt me. Um, okay, uh, so I'll start by, and this is a picture of a time I've only been to the Channel Scablands once, and this is me at Dry Falls. I'm sure many of you have already been there. So I want to just start off by saying that this project that I'm going to talk about was in collaboration with some other scientists that I worked with during my postdoc. So I'm just putting up some of those mascots from these different universities that we all came from. And I'll just share a little background on me, which Dale already shared a little bit. I just started this year as an assistant professor at UC Santa Cruz in California. And before that, I was living in Los Angeles. I was a postdoc at Caltech. And the work that I'm going to be presenting today is the research that I did during my postdoc while I was at Caltech. And so I'm going to be talking about this paper that came out this year in PNAS. Okay, so a quick overview of the talk. I'm going to start with the methods. So I'm going to explain this concept that's called glacial isostatic adjustment, which is what all of my research is about. And the quick answer is that is crustal deformation that happens over the ice age. And after I explain the tools that I use, we'll talk about megafloods and the erosional history of the channeled scablands. And we'll ask whether landscapes respond to crustal deformation over the ice age. Okay, so ice sheets have an influence on a number of surface processes, including landscapes, the atmosphere, and oceans. And in my research, I focus on the interaction of ice sheets with the solid Earth in a process that's called glacial isostatic adjustment. So what is glacial isostatic adjustment? It sounds like a complicated word, and it is a little complicated. So, um, so, uh, so glacial isostatic adjustment refers to kind of a few different processes in which ice sheets interact with the solid Earth and change sea level by interacting with the solid Earth. So ice sheets can change sea level globally through these interactions, and I'm going to focus on this process. And one way that ice sheets can change sea level is that they're so massive that they exert a gravitational pull on the surrounding oceans, causing sea level to be higher in the vicinity of continental ice sheets. And so, for example, here I'm showing the sea level fingerprint, or you can think of this as just the predicted sea level change that occurs from ice melting over Greenland from 2003 to 2016. And so in this figure, you can see that this blue area around Greenland is an area where sea level is actually falling close to the melting ice sheet. And that's happening because as the ice sheet gets smaller, that gravitational attraction is dissipated and water will actually migrate away from a melting ice sheet. Another way that ice sheets change sea level is by deforming the Earth's crust. I'm going to explain this process by kind of backing out and using some analogies. So stay with me while I do a little detour that is we'll think about how we can imagine the Earth's rheology and how like the solid Earth will respond to loading and unloading of ice sheets. So think about a mattress that's a foam mattress that has many layers. And so in this mattress, there is 2 foam layers. There's the upper squishy foam, there's the lower squishy foam, and there's a top part that's just a bendy top part. So what happens when we put a heavy weight onto this foam mattress? Well, at first, the mattress will sink down a little bit, but as the weight sits on the mattress, it'll sink in over time until it gets to however far this weight will sink into the mattress. And then if we take that load or this heavy weight off of the mattress will bounce back. At first it'll bounce back, but as this little fingerprint, this little circle that has the fingerprint shows, it's gonna take some time for the mattress to come back to be fully recovered, right? It's gonna start bouncing back and then slowly come back to its original position. So we're imagining the Earth as a mattress. On the time scale of ice sheets loading and unloading the Earth's crust, so on the order of 1 to 100,000 years, we can kind of approximate the solid Earth as having the same rheological response as a mattress. And that's because even though the Earth is solid, it can actually I think I'll wait to say this for the next slide. So this is kind of our analogy here is the Earth is the mattress that we lie on, and the Earth has a bendy top part and 2 layers of squishy foam, and it has a core. We'll kind of ignore the core. And what that really is there's the Earth's crust, there's the Earth's mantle, and then there's the ooey gooey core that we're going to just kind of ignore in this talk. And so even though the Earth's mantle is solid rock, on long time scales, that rock can flow. And that's actually how we have plate tectonics, is that the mantle will actually flow. So we can model the Earth's response to loads on the Earth as kind of like a foam mattress. So it'll respond, and take some time before it gets to its full response. So, okay, so now we have our Earth and its different layers that have different squishiness. If we put a heavy weight like an enormous ice sheet, in this case, it's 3 kilometers thick, which is how thick the North American ice sheets were around their thickest. The same thing will happen as when we load the Earth, when we load the mattress. So the heavy weight will sink down into the Earth over time. And so, so this is a little cartoon of this process of glacial isostatic adjustment. As the ice sheet sits on the Earth's crust, it will actually push mantle out from beneath the ice sheet and cause that mantle to flow outward to the periphery of the ice sheet, which then becomes uplifted. So I sometimes like to use bread dough. You can see there's lots of different analogies, but I like to think about bread dough as another analogy for this process. So you have, you know, kind of this elastic dough. When you punch it down, it'll go down beneath where you punched, but it'll puff up around. And that's what the solid earth does as you load and unload the Earth's crust with ice sheets. So if we remove the ice sheet by melting it and putting that water into the oceans, the opposite will happen. So the mantle that had been displaced by the ice sheet will flow back beneath the ice sheet and the crust will rebound. And so here on the left, I'm showing a map of present day sea level change due to this process of glacial isostatic adjustment. And on the right, I'm showing this cartoon of how this works. And so on this map, the red areas or the warm colors are areas where sea level is falling due to the process of glacial isostatic adjustment. And the blue areas are where sea level is rising. And so we can see, for example, over Canada, we see this red area here, which is an area where the North American ice sheets used to be, and the crust is now rebounding after the weight of those ice sheets has been removed, and sea level is actually falling in those areas. And there's really nice evidence of that. So here's a photo from Nunavut in Arctic Canada, and you can see these uplifted shorelines that document post-glacial rebound in this area. So all of these shorelines are past shorelines, so sea level used to be higher and sea level has been falling. Okay, hopefully that felt like a good introduction to glacial isostatic adjustment. So I'm going to return back to this little cartoon of how ice sheets interact with different parts of the Earth system, and highlight this interaction between solid Earth and landscapes. And this is an area that's a major part of my research, is thinking about feedbacks between landscapes and this process of glacial isostatic adjustment. So as the solid Earth deforms over the ice age in response to ice sheets loading and unloading the Earth's crust, how are landscapes responding? And can landscapes record some of this crustal deformation? And one of the reasons that is really powerful is that it can be hard to reconstruct ice sheets in the past. Ice sheets are by nature erosive. So as ice sheets grow, they'll just bulldoze over previous evidence of where ice margins used to be. And so that means it can be really hard to figure out where ice margins were before they were at their maximum position. And so by better understanding the interactions between landscapes and this process of crustal deformation that's controlled by ice loading, it might be possible to reconstruct ice sheets in the past, even when you wouldn't need to know where the margins are if you can find out from farther away from the ice sheet how the landscape's responding to those ice loads, because it'll respond differently based on how big or how small that load is. Okay, so that's just kind of an introduction to my research generally. And now we'll dive in to
Tamara, can I ask a question?
Yes.
Can I ask a question?
Go ahead.
Going back to the next chart, which shows the rise and lowering of the sea level, what's going on with the United States? Is that are we?
Oh yeah, that is the peripheral bulge. So this blue area is an area where sea level is rising due to glacial isostatic adjustment. And so in this cartoon, you can see on that bottom part of the cartoon, underneath where the ice sheet was, there's the arrows going up, right? There's the crust rebounding, but on those sides, there's this peripheral bulge and there's arrows coming down. And this is the peripheral bulge is now subsiding as the mantle flows back beneath the former ice sheet. So all of the United States sits on what was the peripheral bulge of the Laurentide ice sheet. And now that that ice sheet has melted away and the crust over Canada is rebounding, the crust around the United States will subside.
Okay, thank you.
Yeah. Yeah, great question, and it'll become important very soon. Trying to get this to go forward. Okay. Okay, so we're going to now apply this tool set to the channel scablands and ask, how has the erosion of the channel scablands changed in response to this process of glacial isostatic adjustment over the course of Ice Age mega flooding? And so I will talk about this paper that I wrote about this. Oh, I recently added this actually. I thought I would do a little bit of an introduction to Ice Age stuff, but it sounds like you guys are already thinking about it. I saw that introduction about Milankovitch theory. So here I'm showing the curve that I'm showing here is a proxy for global ice volumes. So I'm showing benthic oxygen isotope stack signal. And this serves as a proxy for global ice volume over the last 2 million years, shown here. And so this at the left is present day and the right is into the past. And I'm highlighting the last glacial cycle here in this box, where again, present day is on the left, and this peak here on the right is the last interglacial. And so on this curve, the troughs represent glacial maxima, so times of height at the highest amount of global ice volume, and the peaks represent interglacial, so times like today where sea level is relatively high. And we can see that what this curve shows is there's been many glacial cycles over the last 2 million years, here shown here, and so we're going to be focusing on this time period from the last glacial maximum to present day, so the last deglaciation, as continental ice sheets were melting from their maximum extent to the present day. And so just as a bit of an overview, and it sounds like you guys talk about these kinds of things all the time, but here is a map showing what areas were glaciated over North America at the last glacial maximum. There's the Cordilleran ice sheet that was over the Rocky Mountains, and then the Laurentide ice sheet, and they kind of merged in this saddle region. And on the right, I'm showing a curve that shows global mean sea level over the last deglaciation. And so what we can see is that over this time, global sea level has risen steadily, and there are times where global sea level rose especially fast. And so a lot of my research focuses on trying to better reconstruct ice sheets in the past and figure out what ice sheets melted at what times and contributed to global sea level at what times. And as I mentioned before, I see studying landscapes as a way to kind of expand our tool set of how we can try to reconstruct ice sheets in the past. Okay, so I'm going to jump into the scablands. So as you all know, the Channel Scabland is a landscape that's a series of canyons that were formed by dozens of glacial outburst floods from glacial Lake Missoula during the last ice age. And so I'm showing a little schematic here on the right. And so glacial Lake Missoula is over here. You guys probably all know this really well if you're part of this institute. And so these canyons that form the scabland are cut into Columbia flood basalt on an otherwise uneroded, lusk-covered Columbia plateau. And for me, what was really special working on this project is this is really visible even from space. And so here I'm showing, showing a map from satellite imagery where you can see, we can really clearly see the channeled scablands, kind of these darker regions carved into this lighter lusk-covered plateau. And so that was always really fun for me to like go on Google Earth and get to my study site really quickly. And so those darker regions are basalt, that's why they're darker. The lighter is lusk. And this is just an example of what this looks like on the ground. You guys probably get to go look at this every weekend. And so these floods happened from 22 to 14,000 years ago. And I'm including this map of Native American people who lived on this landscape, just to point out that there were people living here at the time who saw some of these floods, and stories of these mega floods are recorded in oral histories and legends. So scouring of the Channeled Scabland likely occurred while the Columbia River was dammed by an advancing Okanagan ice slope. I'm showing just a schematic of this here. And flood deposits suggest the Okanagan ice slope blocked the Columbia River, forming Glacial Lake Columbia here from 18 to 15.5 thousand years ago. And at least 80 flood events occurred during this time. And there are two main channel tracks that were eroded while Glacial Lake Columbia existed. Sorry, I think the timer is on, so it's advancing. I'm showing Telford Crab Creek in blue and Cheney Palouse in orange. And so these are regions that when the Columbia River was blocked by this ice slope, when there were floods coming in from Glacial Lake Missoula, there was overspill into this part of the Columbia Plateau, and these channels were carved. And so there's a number of outstanding questions that remain about how the Channeled Scabland formed. For example, did flood routing change over the course of Missoula mega floods? Were these two main channel tracks carved at the same time? And how big were flood discharges? Were different flood events different sizes? And knowing the answer to these questions helps us to understand how landscapes are carved by outburst floods, both on Earth and on Mars, as well as how floods precipitate abrupt climate events. And so previous studies that have tried to answer these questions have not accounted for glacial isostatic adjustment. And I'm going to ask whether incorporating this process can help us to answer some of these outstanding questions. So as a review, glacial isostatic adjustment refers to solid earth deformation due to the redistribution of surface mass loads as ice sheets grow and melt over the ice age. And the channeled scablands are located right at the edge of the Cordilleran ice sheet, kind of by definition, right? It's from a glacial outburst flood. And so that means that the channeled scablands sit on the ice sheet's peripheral bulge. So that's why that question was important, because where the channeled scablands are located means that they're going to see some of the higher rates of crustal deformation because they're kind of in this area between where the crust would be subsiding and where the crust would be uplifting as the peripheral bulge, kind of that transition between being under the weight of the ice sheet and the uplifted part of the crust. And so glacial isostatic adjustment causes rates of crustal deformation, of on the order of 10 millimeters per year, which is regionally much higher than tectonic uplift rates. So here I'm showing how glacial isostatic adjustment changed topography in the channeled scablands over the time of Missoula mega flooding. So this color bar is showing topographic change due to this process of glacial isostatic adjustment. I'm going to be focusing on this time period from 18 to 15.5 thousand years ago, the time that these scablands were thought to have formed, although 20 to 14,000 years ago encompasses this age uncertainty. Sorry, that's on the auto. Okay, so we're going to see if we can use these predictions of glacial isostatic adjustment to better understand the erosional history of the scablands. And so we're going to use these predictions of topographic change to kind of revisit what flooding would have looked like on this landscape. Okay, so this is the approach that I'm going to take. I'm going to simulate flood routing on topography that's corrected for glacial isostatic adjustment. So I'm basically taking present day topography and correcting for that topographic change that we saw in the previous slide. And then we'll see whether we can, keeps advancing, sorry. Whether we can discover if there were routing changes over time due to this topographic change, and whether we can predict the relative timing of erosion in each of these different tracks. And then ultimately we'll circle back and say whether we can say anything about what flood size was. So here's an example of what the simulation looks like. So this is the predicted water depth over the course of one of these simulations. This is on topography at 18,000 years ago. And so you can see that over these 39 hours, we have these channels are flooding. And on the right here, I'm showing the boundaries that are used in the flooding simulation. So the green lines are the inlet. So water is flowing through there, and that's kind of simulating what glacial Lake Columbia overspill would have been like. And so there's a lot on this slide. So here I'm showing, I've taken those simulations of predicted water depth over the course of a flood, and I've calculated the bed shear stress, which we can think of as the potential to erode based on the predicted water depth and the predicted water velocities. And so each of these maps on the bottom shows the maximum bed shear stress that was achieved over a course of a simulation on each of these topographies. So on the left and the middle, we have over the course of Channeled Scabland formation. So this is corrected for glacial isostatic adjustment. And on the right is present day topography. So there's no glacial isostatic adjustment correction. And on the top here, I'm showing those maps of glacial isostatic adjustment. So just to compare from 18 to 15.5 thousand years ago, what's happening. And we can see there's more uplift towards Cheney-Palouse at 18,000 years ago, whereas there's more subsidence at 15.5 thousand years ago towards the northwest. And on the left here, I'm showing a transect across these maps of topographic change. So we can see there's more subsidence towards Telford Crab at 15.5 thousand years ago. And so we can see that at 18,000 years ago, there's flow in both of these tracks, whereas at Telford Crab, it's mostly concentrated in Telford Crab, and that's because there's been more subsidence towards that side. So water is flowing more into that area. And that's in contrast to on present day topography, where there's similar flow in both tracks. So we can see that glacial isostatic adjustment does change flood routing over the course of Channeled Scabland formation. And here I'm showing the discharge in each of these tracks. So in the blue is Telford Crab and the orange is Cheney-Palouse. And so this kind of just helps us see the same thing, where at 18,000 years ago, there's flow in both Telford Crab and Cheney-Palouse, although there's more discharge in Telford Crab. This effect is pronounced at 15.5 thousand years ago. Most of the discharge is going into Telford Crab, and this is in contrast to, on present day topography, where we see equal discharge in both tracks. So this suggests that glacial isostatic adjustment causes a different potential to erode each tract at these different time steps. Okay, so we're going to take this another step further, and we're going to compare those maps of bed shear stress to the threshold that's required to erode basalt. So we know these channels are formed by eroding basalt, and probably by plucking columns of basalt. And so based on the size of column, kind of pieces of basalt columns that are found in deposits, we can calculate the critical shear stress that's required to like pluck that basalt boulder. And so we can compare the predicted shear stresses to what's required to erode. And what we're going to do is we're going to separate out the shear stresses in Telford crab in blue and in Cheney Palouse in orange. And we're also only going to look at the shear stresses in the basalt eroded regions. So we can kind of use this map of the darker regions versus the lighter regions to focus on just the regions that we know eroded to basalt. Okay, and this dashed line shows the threshold, the minimum threshold to erode basalt is this first dashed line. So at 18,000 years ago, we can see that the height of the distribution of shear stresses is within that basalt erosion threshold for both Telford crab and Cheney Palouse. So we would predict erosion at 18,000 years ago, whereas at 15.5 thousand years ago, that peak for the blue is within the erosion threshold for basalt, but not for the orange. So we'd only predict to erode Telford crab. And that is in contrast to predictions on the present day topography, where we would predict that we would erode both Telford crab and Cheney Palouse. And so if we assumed the present day topography, we might predict an incorrect flood routing and therefore erosional history. And so we can take this another step further, kind of as a check, and look at the, instead of just looking at the basalt eroded regions, we can look at the not basalt eroded regions. So these are the areas that are these lighter areas that were less covered, because we know that those areas did not erode to basalt. And so we would expect that if we look at those distribution of shear stresses, they should be well below the threshold to erode basalt, because we know they didn't erode basalt. And so we can see that at 18 and 15.5 thousand years ago, that's the case. Those peaks are well below that dashed red line. But at present day, at present day, it's predicted that over 15% of these non-basalt eroded or less covered regions would exceed the threshold to erode basalt. And we know that that's not true. So this is another kind of check that shows us that it's more realistic to run our flood calculations on topography that's corrected for glacial isostatic adjustment. Okay, so here is a bit of a summary slide. This figure on the bottom shows the glacial isostatic adjustment corrected spillover elevations between Glacial Lake Columbia and these tracks at these different times. And so the gray is present day, so no correction for glacial isostatic adjustment. The blue is 18,000 years ago, and the green is 15.5 thousand years ago. And on the bottom, I'm showing topographic change due to glacial isostatic adjustment. So you can see that at 15.5 in the green, there's more subsidence in Telford crab, which is allowing more water to spill over into those tracks. Okay, so with that, I am going to summarize, come back to these questions that we asked and see whether we can answer them using the work that I showed. So did flood routing change over time? Yes, flood routing likely shifted as glacial isostatic adjustment changed topography in response to ice sheet melting. Were the main channel tracks, Cheney Palouse and Telford crab, carved at the same time? No, simulations calculating erosional power suggest that the Channeled Scabland formed incrementally. And how big were these flood discharges? Were the different floods different sizes? And this work suggests that earlier floods at 18,000 years ago could have been larger than at 15.5 because at 15.5 thousand years ago, the water is mostly going into one of the tracks. And so you wouldn't need as much water in order to erode that area. But that's something, I didn't include a figure that has a bit more discussion about that. Sorry. Yeah, so this study shows that we can use glacial isostatic adjustment simulations to gain insight into the history of landscapes, and in this case, into the history of channel scabland erosion over the course of mega floods. And this has implications as well for the size of meltwater pulses that would enter the Pacific over the last ice age. And with that, I want to thank my collaborators on this project, and as well as my support. And then I'm going to leave on this conclusion slide to see if there are any questions.
Thank you, Tamara. Excellent presentation. Just fascinating new research on the scabland. Questions from the audience for Tamara?
Well, I have one that I'm just going to see if she has this has to do with Lake Chelan. And I understand this is outside of your study here, but I've always been somewhat fascinated of the depth of Lake Chelan. Was that really ice? Was that really glacial carved to the depth, or was there a major valley there before the glacier that created was there, and the glacier basically filled that valley and maybe carved a little bit? I find it hard to understand looking throughout a great Northwest and the state of Washington, British Columbia, where there's no other lake that's similar to that depth. Is that, I know it's out of your purview of your talk today, but are you familiar with Lake Chelan?
So I'm not that familiar. I think I know where it is. I didn't know that it was especially deep. So I can say some things, but they are probably not going to answer your question. I guess, you mentioned, could it have been carved? Could it have already been deepened before a glacier entered it? And one thought is it could be over many cycles that the glacier would have deepened it. And I think that tends to be, ice will flow into valleys and then keep eroding, right? Glaciers can be very erosive, and so maybe it is over deepened by a glacier. I don't know. Yeah.
Okay.
There is a question about the elevation difference, and I can pull up this plot. I don't have a perfect answer for you, but here's the elevation profile. This is on present day. So this is there, Cheney Palouse is on average lower elevation than Telford Crab, and that difference is different with glacial isostatic adjustments, but I think that's reversed at 18,000 years ago, that this is slightly higher on average, but hopefully that helps. And how far from the edge of ice would the forebulge extend? And so that's a great question. There's some great questions coming in. So the question about how far from the edge of the ice would the forebulge extend? So the shape of the forebulge is, let's see how far I have to go just to see this. The shape of the forebulge is determined by the total load of the ice sheet. And so it actually doesn't matter exactly where the ice margin was, as much as where was the kind of overall thickest part of the ice sheet and how much did that depress the crust. And so that will determine where it goes to the forebulge, if that makes sense. So it's not related to the exact geometry of the ice sheet, but rather how thick the ice sheet was and over what spatial scale it was that thickness. So in some ways, that edge, the peripheral bulge is more sensitive to what's happening way north of the ice margin, because that's where the mass of the ice is, the thickest mass is. And how far does the forebulge extend? We saw on that map of glacial isostatic adjustment that, let's see if I can get back to this quickly. That here we're seeing it's all the way to the Caribbean is the forebulge. It's not the highest part of the forebulge is closest to the ice sheet. It's not like a perfect like half circle. It looks more like that, if that makes sense. Like it's steep at towards the edge of the ice sheet and then kind of comes out like that. So it's the peripheral bulge still exists in the Caribbean, but it's pretty small at that point. But I would say that's the end of the forebulge, as close to the Caribbean. And then, was the Okanagan lobe heavy enough to affect isostatic adjustment? Yes, maybe. So in the modeling I did, it is heavy enough. The question of how thick the Okanagan ice slope was, my understanding is it's not fully constrained, and people debate how thick it was, so that would determine how much of an impact it would have in terms of isostatic adjustment on the Waterville Plateau. In my modeling, the ice slopes were a significant load and kind of impose. You can imagine there's the main peripheral bulge that's due to the full weight of the Cordilleran ice sheet. And then these ice slopes are sitting on top of that. And so you kind of get this kind of complex spatial pattern. There's kind of a forebulge superimposed on another forebulge. But that's a good, very good question. And yeah, can I put the reference? I can definitely do that in a second. I refer to the critical shear stress. Basalt is usually highly fractured, so does it actually fail in shear? Also, there is a different failure mode in the columnar and entablature formations. Great question. You guys are, the best questions to ask. So, well, I'll start with the question about columnar versus entablature. We used the critical shear stress that's estimated for plucking a basalt, a block of basalt of the size that was found. And so we assumed, entablature part would be harder to erode. And so you would have a different critical shear stress if you assumed it was the entablature part. And that, I would say, is a part of the uncertainty in these predictions, is that we estimated that range of the threshold for erode based on plucking columnar basalt. And it would be different. It would probably be more difficult you would probably have a higher critical shear stress. And you're right that it's, so the critical shear stress is not about the energy it takes to fracture the basalt, but rather if it's already fractured, like just to pull off a bit of it. So I believe that is, I hope that answers the question. What's the difference between global sea level and glacial isostatic? Yes, great question. So you'll notice on this map that there's nowhere on this map that is exactly 0. And what that means is that glacial isostatic adjustment does change sea level from the global average everywhere on the globe. But there are places that are quite close to 0. So places near the equator are pretty close to global eustatic sea level change. and then the rest of the areas are areas where that's the reason I have a job, is that we have to correct for glacial isostatic adjustment in order to correctly predict where sea level was at these different parts of the world. And you know, this, I would say the biggest signals are close to the ice sheet. So that's where glacial isostatic adjustment corrected sea level is most different from the global average, is places close to the ice sheets. How responsive is isostatic adjustment to increases or decreases in ice volume? I'm not sure what IOW. Is there a lag time at terminations?
In other words,
Oh, in
IOW.
other words, okay. At terminations, has isostatic depression reached its maximum? Great question. So there is a lag time, and that is kind of that, what I was going with the mattress analogy, is because there is a lag time, because from the time that you load the Earth to when it reaches its equilibrium depends on the viscosity of the Earth's mantle. And so that's kind of how much is the Earth's mantle able to move, how quickly can it move? And around the Earth, that time scale is something of like 1 to 15,000 years. In most areas, it's close to 10,000 years before you get to that, what you're saying here of maximum isostatic depression. The ice sheet would have to sit around for about 10,000 years. And so at terminations, I love this question. Has isostatic depression reached its maximum at a termination? So that depends how long the ice sheet was sitting around at its maximum thickness before the termination. If you think that the ice sheet grew early in the ice age and sat around for the next, you know, maybe it was fully glaciated by 80,000 years ago or like 70,000 years ago, and you think the ice sheet sat around, then yes, it would have reached its maximum by 26,000 years ago. But a lot of the research I do suggests that at least North American ice sheets grew very quickly leading into the last glacial maximum, which means that they did not reach an equilibrium, isostatic equilibrium. And so they would just be continuing to respond to that growth and loading, even as the ice sheet starts to melt. So you kind of get this superposition of it's responding to the loading, right? It's depressing the crust, but the ice is starting to melt. So then it's starting to rebound, and kind of a complicated superposition of these signals.
Yeah, I think the ice sheets reach, you talk about the glacial maximums, and the maximums came towards the end. When things started to fall apart, there was some big bursts of growth, even though the ice sheets were kind of getting into a stage of being kind of weak or ready to collapse. So
I wonder, are you referring to around Washington that there's?
Oh, no, all over Laurentide ice sheet.
Okay, I think
European.
that I think the Laurentide ice sheet reaches its maximum close to 30,000 at different
All
parts
right,
at different times.
Yeah, 30,000 a little after.
Yeah,
And then there was some, you started getting, some warming and pluvials, and even though things were starting to really, the house of cards was beginning to crumble. But at the same time, you had some bursts of, extra growth. And so I'm wondering if when the maximum sizes came at the end, if and I think your answer about 1 to 15,000 years kind of tells us whether there was more isostatic depression. If it reached its maximum at the same time that the terminations were, beginning.
Mhm. Yeah.
Yeah.
Yeah. No, I think you're right that that timescale does line. The ice, it's hard to say because it's like, got to LGM position at different places at different times, and also I'm sure the thickness too. But I
Yeah.
think that timescale around 10,000 years would line up with what you're saying, that it's getting close to that maximum isostatic equilibrium during the course of over the termination, like from 30 to 20,000 years.
Mhm. Thank you.
Yeah, there's lots of really good questions. The question about what is sea level rise rate on the West Coast, honestly, I do not know an exact number, so I'm going to refer you to look online. But I I wouldn't want to give you a very wrong number. What would be the effect of Holocene sea level rise? And also, while I'm answering these questions, if Dale, if you want to add that link to the paper, maybe you know where it is, because I can add it, but I'll do it after I answer the questions.
Sure. Yeah. Unfortunately, I'm not sure I know where that link is, Tamara.
Okay, I'll actually, okay, this is, I'll just type, this is my research website.
Okay.
And if you go to publications, then you can click on the link. It'll actually just go straight to the paper. So you can just download the paper. Okay, in the meantime, I'll keep doing the, so what would the effect of Holocene sea level rise loading the crust and influencing crustal subsidence in the plateau? So I think the question is, sea level is rising and it's loading the oceans close to Washington. Does that influence the crust in Washington? The answer is maybe a little bit, but it's very small compared to the impact of the ice sheet loading and unloading. You can think of just kind of that magnitude of like it being proportional to the magnitude of the thickness of the load. So the Cordilleran ice sheet is, over a kilometer thick, whereas sea level has maybe changed 100 meters, close to the coast. And so it's a smaller, there will be an impact, but it'll be small compared to the effect of the ice. I'll explain the plucking effect. These questions are getting tougher. So there have been studies done kind of experimentally on the shear stress that's required to, there are different types of experiments. Some are, what's the stress that's required for a certain particle of rock to get entrained in water and transported. And so this is something that I would say, I cite in this paper. So you can read more in this paper, especially I think it's in the methods section and the supplement that describes like where we get these values from. But it's from studies that have kind of tried to estimate like what the relationship is between shear stress and like types of rocks. And because kind of a debate in the geomorphology community is, is erosion maybe the threshold is what it takes to start plucking the rock. So not necessarily transporting it, but just starting to like get it off the rock, right? Like you have something that's already fractured. What does it take to pull that off? And so I'm going to refer you to the references in the paper for the details. That's not work that I do. Is there glacial rebound still happening in the Great Lakes region? Yes, there is. Is Ron, thanks, is it that you got the paper? Is that? Okay, any other questions? I can find the link. Does anyone still need the link? Oh, Dale, I think you're muted.
It seems like we have your website there, tamarapico.com. So if everyone will make sure they have that, then that should solve the problem with the link. Any other questions for Tamara?
I have one. One thing I didn't really fully get from was the east-west phenomenon of the flooding. I mean, I got what you described as happening, but really, I guess it's like some of these other questions. It's the loading. What loading caused that east-west phenomenon?
Yes, so this is from the question about if the Okanagan ice slope is important. This is where it comes into play. And so we can see here, you can see this gradient from blue to the red. That's that overall kind of general peripheral bulge of the Cordilleran ice sheet is that gradient. And then these, oh, this timing thing is really annoying. And then the reason that you get this gradient is actually because there's a few different ice slopes. I'll go back actually to show on this. There's this Purcell ice slope and the Okanagan, and so you're kind of squeezing between it. So you're getting so that's what's causing this pattern of deformation.
Yeah, I noticed as you were going through this, the third from the left, the 15.5 Ka. If you just really look carefully at that, the dark blue has come down. So it isn't just that there's a blue on top and red on the bottom. There's been a shift there, and that's due to the ice then. Is that right?
Yeah, that's right. And so sorry, this timing thing, it's we had to do like this automated talk thing for a conference, and I've never been able to get rid of that. So yeah, that's right. And what's happening here is that isostatic, getting closer to isostatic equilibrium. So the Cordilleran ice sheet reaches its maximum close to 18,000 years ago. And as it sits there, as ice sits there, it's this like depression it's kind of adjusting. And so that's right, that this is extending farther south.
Thanks.